Welcome back to Basic Electronics. In the last lecture, we looked at the transition table for a JK flip-flop and worked out the output waveforms with some given input waveforms for a single JK flip-flop. We will now take simple circuits consisting of more than one JK flip-flop and see how the various waveforms can be obtained by following a systematic procedure. We will then consider another commonly used flip-flop, the D flip-flop, and see how we can make a shift register with D flip-flops. Okay, let us get started. Another example. Here are two flip-flops. They are edge-triggered flip-flops because we have this triangle here, and they are positive edge-triggered flip-flops because we don't have a circle just before the triangle. Alright, here is our problem. J1 and K1 are equal to 1, so these two inputs are tied together to 1, and we assume that Q1 and Q2 are both 0 initially, and then this clock is applied, and we want to figure out what Q1 and Q2 would look like with time. This is our transition table. Alright, now in this case, since J1 and K1 are both 1, we are looking at this row of the table. Qn plus 1 is Qn bar. That means Q1 is going to toggle after every active clock edge. It's going to change after this edge, after this edge, after this edge, and so on. So that is what it looks like. It was 0 to begin with, given here, changes here, changes again, and so on. Getting Q1 was straightforward because the inputs to this flip-flop, J1 and K1, were not changing with time. They were always constant, equal to 1, and therefore we could figure out in advance what's going to happen to Q1. With the second flip-flop, the situation is different. J2 is the same as Q1, K2 is the same as Q1 bar, and since Q1 changes with time, like that, these inputs also change with time, and therefore it makes it a little more complex. And we now need to look at J2 and K2 values just before the active edge, that means these edges, to determine the next value of Q2. So let us do that. And we will find it very convenient to have a table listing J2 and K2 at the various transition points to figure out the next Q2 value. So let us prepare such a table there, and let us understand what this says. Here is our T, T1, T2, T3, T4, T5. T1 refers to this active edge here, T2 refers to this active edge, and so on. These are J2 and K2 values at Tk minus. For example, in this row, this value refers to J2 at T equal to T1 minus. What is T1 minus? This is T1. T1 minus is the time just before that edge. And for that, we have J2, which is the same as Q1, equal to 0, and K2, which is the same as Q1 bar, equal to 1. Since J2 is 0 and K2 is 1, J2 is 0, K2 is 1, Q2 is going to be 0, and since it is already 0 to begin with, we are not going to see any change like that. Alright, now the next change can happen at the next active edge, which is T2, and we need to look at J2 at T2 minus and K2 at T2 minus. This is our T2. T2 minus is just prior to that, and at that time Q1 is 1, therefore J2 is 1, K2 is Q1 bar, so therefore that is 0, and we are now looking at J equal to 1, K equal to 0, so Qn plus 1 equal to 1. So the next Q2 is going to be 1, and that is what we see over here. And you can figure out the rest of these transitions in a similar manner. The important thing to note is we always look at J and K values just before the active edge. Here is a more complicated circuit. We have 3 flip-flops now, 1, 2, 3, and all of them are edge triggered, and they are negative edge triggered because we have this circle here. The output of this flip-flop is called Q0. So these would be J0 and K0. This would be Q0 bar. Similarly, we have J1, K1, Q1, Q1 bar, J2, K2, Q2, Q2 bar here. J0 is connected to 1, so it is always equal to 1, does not change with time. K0 is the same as Q2. J1 and K1 are tied together and they are equal to Q0 bar. J2 is the same as Q0 and K2 is equal to Q1 bar. So these are our connections. This is the clock input, and we are also given that Q0, Q1, Q2 are all 0 to begin with. And let us see now what happens. Since the same clock is going to all 3 flip-flops, like that, we know that all transitions in Q0 or Q1 or Q2 are going to happen only after these active clock edges, which are marked here with arrows. And now let us proceed with the first transition, that is after this first active edge. Let us try to figure out what Q0, Q1, Q2 are going to be after T1. And we will find this table very convenient. Let's first understand what it is doing. We have T1, T2, T3, T4, T5 here. Those are the active edges, T1, T2, T3 and so on. This part of the table corresponds to Tk minus. That means just prior to T1 or just prior to T2 and so on. This part of the table corresponds to Tk plus. That means just after T1 or just after T2 and so on. Alright, let us start with T equal to T1, and at T1 minus we have Q0 equal to 0, Q1 equal to 0 and Q2 equal to 0. And knowing that, and knowing all these connections for J0, K0, J1, K1, etc., we can figure out what each one of these is going to be at T1 minus. J0 is always 1, K0 is the same as Q2, and Q2 is 0 at T1 minus, so therefore K0 is 0. J1 and K1 are tied together and they are equal to Q0 bar. Since Q0 is 0, Q0 bar is 1, so that's why we have J1 equal to K1 equal to 1. J2 is the same as Q0 and that is 0 at T1 minus. K2 is the same as Q1 bar at T1 minus, and since Q1 is 0, Q1 bar is 1, so therefore K2 is 1. What we can do now is to predict Q0, Q1, Q2 at T1 plus. So we can fill up this column here knowing these J and K values. For example, J0, K0 are 1, 0. That brings us here, and that says that Q0 is going to be 1, like that. What about Q1? J1, K1 are 1. That means Q is going to toggle. So over Q1, which was 0 earlier, will now become 1. What about Q2? J2 is 0, K2 is 1. That brings us here. So the next Q2 is going to be 0, like that. So what we have now is Q0, Q1 and Q2 at T1 plus. That means just after T1. And we know already that nothing is going to happen to Q0, Q1 or Q2 until the next active edge comes. That means between these two active edges no further change is going to happen, and therefore we can go ahead and plot these three values like that. So Q0 is 1, Q1 is 1, and Q2 is 0. Alright, now that brings us to t equal to t2. At t2 we have these same values here, 1, 1, 0. We are talking about t2 minus now. Note that minus there. And once again we can figure out what J0, K0 are at tk minus, and so on. And then go ahead and predict Q0, Q1, Q2 at t2 plus, etc. So we keep following this procedure, and then we have the complete waveforms. So here are the waveforms all the way up to t5, and the corresponding jk values are also given in this table. And you should really go through each of these entries, the ones that we did not look at already. Figure out why this J0, K0 is 1, 0 here, why this J1, K1 is 0, 0 here, and so on. And why these give rise to this prediction of the next Q values. And that will surely reinforce your understanding of the JK flip-flop transition table. Let us now discuss something called the asynchronous inputs. And the meaning of this term, asynchronous, is something which is not related to the clock. And we will see why these are called asynchronous inputs. Let us make a few points first. Clock flip-flops are also provided with asynchronous or direct set and reset inputs, ST and RD, which override all other inputs, that is J, K, and clock. And these inputs are called preset and clear respectively. So ST is called preset, RD is called clear, and we will see why that terminology has come about. Alright, the ST and RD inputs may be active low. In that case they are denoted by ST bar and RD bar. The asynchronous inputs are convenient for starting up a circuit in a known state. So that is why they are provided. Also, as we will find out later, these inputs can be used for making up counter circuits, some of the counter circuits. Alright, let us look at how these SD and RD inputs work. When SD and RD are both 0, these 4 entries here, that corresponds to the normal operation of the flip-flop. We have this active edge. Since it's a positive edge triggered flip-flop, we have this rising edge here of the clock. And these 4 entries we have already seen earlier. So that is the normal operation of the flip-flop. When SD is 0 and RD is 1, then Q becomes 0, irrespective of these 3 input values, and that is why we have shown these as don't care conditions, that is X. And now it is clear why these inputs SD and RD are called asynchronous, because the operation is not related to the clock. These inputs simply override the clock. When SD is 1 and RD is 0, then Q becomes equal to 1. Again, irrespective of these other 3 inputs, and SD equal to RD equal to 1 is not allowed. Now imagine that we have a bunch of JK flip-flops of this type in our circuit, and we want to make them all equal to 0 in the beginning. Now that can be done by simply making RD equal to 1 and SD equal to 0 for all of them. That will force all the Q outputs for the flip-flops to be 0. And similarly, we can force Q equal to 1 by making SD equal to 1 and RD equal to 0. So that is why we said the asynchronous inputs are convenient for starting up a circuit in a known state. Another useful flip-flop is the D flip-flop, and it can be a positive edge triggered flip-flop or a negative edge triggered flip-flop. It has two inputs, D and clock, and the convention for the clock is similar to what we already seen. This triangle indicates that it's an edge triggered flip-flop, and this circle here indicates that it's a negative edge triggered flip-flop. We can think of a D flip-flop as a JK flip-flop with K equal to J bar, and that input is taken as D. This is a possible implementation of the D flip-flop. And if this is a positive edge triggered flip-flop, then so is this. If this is a negative edge triggered flip-flop, then so is this one. And keeping this equivalence in mind between the D flip-flop and the JK flip-flop, it is easy to figure out the transition table for the D flip-flop. Let us consider D equal to 0 first. What does that mean? That means J is 0 and K is 1, and that means after the active clock edge, Q is going to become equal to 0, and that is what it says over here. Similarly, if D is 1, then J is 1 and K is 0, and then after the active edge, Q is going to become equal to 1, and that is what it says over here. So if D is 0, Qn plus 1 is 0. If D is 1, Qn plus 1 is 1. And the same table is also valid for this negative edge triggered D flip-flop, except of course for the active edge, which is a negative transition now. Let us look at these waveforms now to understand the operation of a D flip-flop. This is our clock waveform, and the active edge is marked with an arrow. In this case, it's a positive edge. This is our D input, and let us see what happens as a result of this input. At T1, what do? We look at the D value just before this active edge, and we find that it is 0, and therefore the Q output just after T1 is going to be 0, and then of course it does not change until the next active edge arrives. So therefore Q is 0 throughout this interval. What happens at this point? At T2, we look at the input D just before T2, that is T2 minus, and we find that D is 1, and therefore just after T2 our Q is going to become equal to 1, and then it's not going to change again until T3, and so on. Let us look at these waveforms now for the negative edge triggered D flip-flop. Here is our clock. The active edge is now the negative clock edge. This is our D input, and at T1 we are going to look at D just before the edge, and we find that D is 0. So therefore our Q is going to be 0 after T1, and then it's going to stay equal to 0 throughout this interval. At T2, or rather T2 minus, we find that D is 1, and therefore our Q is going to become equal to 1 after T2, and then it's going to stay equal to 1 up to T3, and so on. Alright, let us summarize. The D flip-flop can be used to delay the data signal by one clock period. So this D is called the data input, and that's why it is denoted by D. And what is this delay that we are talking about? Let us compare this waveform and this waveform, and we see that this output is a delayed version of the input, and the delay is one clock period, and the same thing happens here as well. With J equal to D and K equal to D bar, we have either J equal to 0, K equal to 1, or J equal to 1, K equal to 0, and therefore the next Q is 0 in the first case and 1 in the second case. This we have already discussed. Instead of a JK flip-flop, an RS flip-flop can also be used to make up a D flip-flop with S equal to D and R equal to D bar. Let us now look at a shift register. which can be made up with D flip-flops. In this example, we have 4 of them. The output of the first flip-flop is called Q1, the second Q2, then Q3, and then Q4. The clock is common to all of them, and that is shown over here. This D input is applied to the first flip-flop. So this D is shown over here, and that is connected to this D1. The output of the first flip-flop, Q1, is connected as D2. Similarly, Q2 is connected as D3 and Q3 is connected as D4. And now let us see what happens as a result of these inputs. To begin with, we have Q1 equal to 0, Q2 equal to 0, and so on. And that is also indicated over here. So all Q values are 0. And now the first active edge comes along, this one. And let us see what happens. Remember, we have to look at the D input of each flip-flop just before the active edge. Now for this flip-flop, the D input is this D here, that waveform, and just before this active edge, its value is 1. So therefore, Q1 is going to change to 1, and then it's not going to change up to the next active edge. Alright, what about Q2? For this flip-flop, Q1 is the D input, and therefore we should now look at the value of Q1 just before the active edge, and we find that it is 0. Therefore Q2 is going to remain 0, and again it's not going to change until the next active edge. And the same thing will happen to Q3 and Q4 as well. So this is what we have after the first active edge. Q1 has become 1, Q2, Q3, Q4 have remained equal to 0. And that's also indicated here, 1, 0, 0, 0. Alright. Now after the second active edge, what is Q1 going to do? We need to look at D just before that active edge. D is 1, so Q1 will be equal to 1 after T2, or after this active edge here. What about Q2? We now look at Q1 because that serves as the D input for the flip-flop here, and Q1 is 1 just before the active edge, and therefore this Q2 is going to change to 1, and then of course it's not going to change until the next active edge. What about Q3? For Q3, Q2 serves as the D input, which was 0 just before the active edge, so therefore Q3 will stay equal to 0, and similarly Q4 will stay equal to 0, like that. So now we have 1, 1, 0, 0. And we can proceed in this same manner and see what happens. And we're not going to go through each step now, but just look at the results. So this is after the next active edge. And so on. And we observe that each output is a delayed version of the previous output. So for example, Q3 is like this, and Q4 looks exactly like Q3, except it has got delayed by 1 clock period. That is one observation that we make. And also this D flip-flop has synchronized the transitions with the active edges. For example, our D input was not synchronized with the clock. These changes were not at the same time as the clock edges, but because of this D flip-flop, the first D flip-flop, output Q1 has got now synchronized with the clock edges. So that is how a shift register works. And you can try out this simulation. The circuit file is available. To conclude, we have seen how the circuits made up of JK flip-flops can be treated in a systematic manner. and the output waveforms can be obtained. We have looked at another flip-flop, the D flip-flop, which may be considered a special case of the JK flip-flop with J equal to K equal to 1. We have seen how D flip-flops can be connected to make up a shift register. In the next class, we will look at how a shift register and an adder can be used to make a binary multiplier. That is all for now. See you next time.